You know, when you click a button on your computer, it just works. It feels like magic, right? But what's really going on in there? Well, it's not magic. It's actually this incredible high-speed symphony. And today, we're going to pull back the curtain and show you exactly how it all comes together. Let's dive in.
So here's the game plan. First, we'll look at the main parts. Then, we'll meet the brain, the CPU. After that, we'll dive into computer memory, figure out the core process that makes everything tick, and finally, see how all these pieces communicate. Sound good? Let's go.
Okay, section 1, inside the computer. We're going to start with the stuff you see every day, and then, peel back the layers to get to the really cool stuff happening inside.
Seriously, think about it. You click, you type, you swipe all day long without a second thought. But that one single mouse click, it kicks off this incredible chain reaction, happening at speeds that are almost impossible to imagine. And that's exactly what we're going to break down right now. So, when it comes to hardware, you can basically split it into two groups. You've got your external stuff, the keyboard, the mouse, the monitor, the things you can actually touch and see. But the real action, where all the thinking happens, that's all internal. So, let's metaphorically crack open the case and get to the good stuff. All right, section 2. We are going straight to the top, to the master of operations, the CPU, the central processing unit. I mean, it's simple, really. If your computer were a person, the CPU would be its brain. It's that important. And there it is. Looks kind of simple, right? Just a small square. But don't let that fool you. This little thing is the absolute command center of your entire computer. Every single thing your computer does, from opening a file to playing a game, has to pass through this chip. It's the engine that makes the whole car go. But here's where it gets really interesting. The CPU isn't just one monolithic thing. Nope. It's more like a highly specialized team, all crammed onto that one tiny piece of silicon, working together perfectly. So, let's meet the crew. First up, you've got the control unit, or CU. This is the manager, the boss. Think of it like a traffic cop for data. It doesn't do the math itself, but it fetches the instructions and tells all the other parts what to do, and in what order. It's directing the entire show. Then you have the arithmetic logic unit, the ALU. Now this is the calculator of the group. It's the number-crunching powerhouse. All the math, addition, subtraction, you name it, happens here. But it also does logic, like comparing two numbers to see which is bigger. This is where the heavy lifting of computing actually happens. And last but not least, we've got the registers. Okay, imagine you're an accountant. Would you keep your calculator on your desk or across the room? On your desk, right? It's just faster. That's what registers are. They're like a tiny, super fast scratch pad right on the CPU itself, holding the exact numbers the ALU is working with right now. So, we've got this amazing brain, the CPU. But what good is a brain without memory, right? It's pretty useless. So for our next section, let's talk about where the computer stores all its thoughts and the information the CPU needs to actually do its job. When we talk about computer memory, there are really two main types you need to know about. First is primary memory, which you probably know as RAM. Think of RAM as your short-term memory. It's incredibly fast and holds everything you're currently working on. But, and this is a big but, the second you turn off the power, poof, it's all gone. That's why we need secondary memory, like your hard drive or SSD. This is your long-term memory. It's slower, sure, but it holds onto your files forever, even with no power.
But hold on. There's actually a secret weapon in the memory game: cache. Here's the deal. Even though RAM is fast, the CPU is just astronomically faster. Making the CPU wait for RAM is a huge bottleneck. So engineers came up with a brilliant solution. They put a tiny, ultra-fast piece of memory called cache right next to the CPU. It acts like a VIP express lane, holding the data it predicts the CPU will need next. It's a total game changer for performance.
All right, we've met the brain, the CPU. We've met its memory. Now, it's time for the main event. How do these parts actually talk to each other to get anything done? Well, it all boils down to this incredibly simple, super elegant four-step dance that happens billions of times every single second. And this right here, this is it. This is the fundamental heartbeat of your computer. It's called the instruction cycle. And get this, every single thing you do, every click, every key press, is broken down into millions of tiny little instructions, and every single one of them goes through this exact same four-step loop. So let's break down this little dance. It's super simple. Step 1 is fetch. The control unit goes out and grabs the next instruction from memory. Step 2 is decode.
The CU looks at that instruction and figures out what on earth it's supposed to do. Step 3, execute. The instruction gets passed over to the ALU, which does the actual work, the calculation. And finally, step 4, store. The result of that calculation gets saved back into memory or a register. And that's it. Fetch, decode, execute, store. Over and over and over again. Billions of times a second. That's computing.
Okay, so we've got all these incredible parts, the CPU, RAM, all that. But how do they actually talk to one another? How does data physically get from point A to point B? To answer that, we need to look at the computer's internal information superhighway.
This is it, the system bus. It's literally a set of wires, or pathways, on the motherboard that connects everything together. Just think of it like a highway system. It's what lets the CPU, the memory, and all of the other components send information back and forth at blistering speeds.
And just like a real highway, this bus has different lanes for different jobs. You've got the address bus, which is basically the GPS. It tells everyone where the data is supposed to go. Then there's the data bus, which is the lane that the actual data travels on. And finally, you have the control bus. That's like the traffic signals and the police, sending out commands and timing signals to make sure all the traffic flows smoothly and doesn't crash.
Now, here's a pretty cool side note. It turns out not all CPUs are built with the same philosophy. There are two main schools of thought. On one side, you have CISC, which stands for Complex Instruction Set Computer. These chips use really powerful instructions that can do a lot in one go. On the other side, you have RISC, or Reduced Instruction Set Computer. These guys use a much smaller set of super simple, super fast instructions. It's a classic trade-off, really. Do you want a few powerful commands or tons of simple, fast ones? It's why the chip in your phone is probably designed differently than the one in a massive server.
So when you put it all together, what do you get? You realize that a computer isn't just one part doing all the work. It really is a symphony. The CPU is the conductor, waving the baton. The memory is the sheet music, holding all the instructions. And the system bus is the very air that carries the sound between the musicians. It all has to work together perfectly to create that smooth experience we just expect every day.
And when you boil it all down, it comes back to this one fundamental idea. The processor's entire job is to execute instructions. That's it. It's just an incredibly fast and obedient servant following command after command after command, and in doing so, it builds our entire digital world. Just stop and think about that for a second. That whole symphony, that fetch, decode, execute, store cycle is happening billions of times every single second inside a device you can hold in the palm of your hand. It's absolutely mind-boggling when you really think about it, and it makes you wonder, right? If this is what we can do today, what in the world will the next generation of processors be able to achieve?